Welcome to the Teaching Company's lecture series on high school chemistry. My name is Frank Cardula. Several years ago, the Teaching Company decided to expand their offerings to include a few high school courses in addition to their normal college selections. One course they wanted to offer was chemistry. They invited high school teachers from across the nation to submit what at that time were videotapes of their teaching. I was fortunate enough to be chosen to prepare the original series of lectures. The series appears to have been pretty well received, and I have certainly cherished the emails that would occasionally arrive from students thanking me for helping them through what was often a course in which they had been struggling. And on a few occasions, even a phone call from an entire class of students who apparently had been using the videos to supplement what they were doing in class. But time, of course, marches on, and so has the Teaching Company. Several months ago, I was contacted and asked to expand and revise the original series of lectures to both increase their usefulness so that they might incorporate some of the more sophisticated video and graphical capabilities that are now available to all presenters at their studios in Chantilly, Virginia. With these goals in mind, this new series was prepared. We're going to be spending considerable time together over what I assume will be a period of several weeks, if not months. We will be focusing most of our attention on what, for lack of a better term, might be called the problem-solving aspects of high school chemistry. For what has always appeared to me to be somewhat mysterious reasons, many high school students often have a lot of difficulty solving what might appear to be very simple elementary problems in chemistry. Indeed, it is this aspect of the high school course that typically turns them off to chemistry in particular, sometimes science in general, and even more seriously, leads some of them to conclude that in some odd way, they are personally lacking in some aspect of mathematical intelligence or ability, when such is definitely not the case. So that brings us to what we might call the key ideas upon which these lectures rest. Obviously, in a series of 36 half-hour lectures, it's not going to be possible to cover every single thing that would be covered in an entire full-year high school chemistry class, so we had to make choices. We decided that the main focus and goal of these lectures would be to help beginning or struggling chemistry students better understand, and the key word is understand, what you will probably be expected to understand in a first-year high school course. This first lecture has only one purpose: to try and convince you that even though it is often tempting to try and take what at first glance appears to be the easier road to solving chemistry problems, these easy roads too often lead to nowhere. And what you need to do is work at achieving a really meaningful understanding of the concepts and the quantitative thinking operations that underlie most high school chemistry problems that students are asked to solve. In lectures 2 and 3, we look at these quantitative reasoning operations in more detail. And then in lecture 4, we see how they apply to a relatively simple concept like density. Lectures 5 and 6 are devoted to the metric system and conversions both within and between this system of measurement and the English system. Perhaps not the most exciting bridge, but certainly a necessary bridge that must be crossed and understood. Lectures 7, 8, and 9 introduce some preliminary ideas and vocabulary that will be needed for some of the later material. In Lecture 10, the mole is introduced, with Lecture 11 devoted to solving mole problems. Lecture 12 deals with something called Avogadro's hypothesis and the concept of molar volume. Lectures 13 and 14 are devoted to solving some classic percent composition and empirical formula problems. Lecture 15 covers how to balance chemical equations and what you are actually doing when you balance them, which then leads us to lectures 16 through 18, devoted to what are called stoichiometry problems, the core of many quantitative aspects of many high school courses. We then devote the next 3 lectures, numbers 19 through 21, to molarity, both the concept and typical problems, which will in turn allow us to begin our study of equilibrium, various aspects of which pervade most of the remaining lectures. Lectures 22 and 23 introduce us to general principles of equilibrium. Lecture 24 covers the equilibrium constant and how it should be interpreted. Lectures 25 and 26 are devoted to Le Chatelier's principle. And in Lecture 27, we begin to learn how to solve equilibrium problems. Lecture 28 deals with the self-ionization of water and pH, which allows us to discuss strong acids and bases in lectures 29 and 30, weak acids and bases in lecture 31, and titrating acids and bases in lectures 32 and 33. The last two formal lectures, numbers 34 and 35, are devoted to solubility equilibria, while the final lecture pulls concepts from several other lectures and serves as a review of much of the material that was covered. And as I said, the focus throughout will be at achieving understanding, because in my view, without understanding, no real learning has taken place. Once we decided that that was going to be the philosophy upon which the lectures would be based, things followed from that. For example, when we had to decide what we would talk about in a given lecture, it was very tempting, I'm being a chemistry teacher, to want to come in here with a lot of, whiz-bang, wow stuff. Chemistry lends itself to explosions and colors and fire, and oh boy, that's fun. And it's fun for the teacher too, because we love to enthrall and entertain and wow our students. But that's not what you need. That may be fun, but that's not what you need. I will be doing several demonstrations that will illustrate and clarify the concepts we're trying to understand, but we'll leave most of the whiz-bang, just for fun stuff to either your current chemistry teacher or to other commercial products that emphasize these kinds of things. Demonstrations, of course, require both equipment and chemicals, and I'm deeply indebted to Glenbrook South High School in Glenview, Illinois, Jeff Rylander, the chair of the science department, and Kelly Timpson, one of their chemistry teachers, as well as Niles North High School, where I spent the bulk of my teaching career, Lois Wisniewski, the director of science, and especially John Kretzis, one of my former students who now teaches the very course that he sat in several years ago. Another component of high school chemistry is laboratory work. While we obviously can't do labs together, you hopefully are obtaining this experience in your current course. If you're not actually enrolled in a high school course, all is not lost. Do a Google search using the words chemistry, home, and experiments. You will find an enormous number of sources for laboratory experiments you can do at home with common chemicals. I got 2,260,000 hits when I used these three search words that I mentioned. In brief, I'm here to help you understand what you may be hearing in your class or what you may be reading in your textbook. Not only to help you solve chemistry problems, but to help you to really understand how to solve them and what you are doing when you solve them. I've been fascinated over the years to watch students as they struggle and eventually learn how to solve what are basically very simple elementary problems. Why do so many students find high school chemistry so difficult? I have spent years pondering this question. I think I've found at least a major part of the answer. If I were to summarize everything I've learned over the years, I think I can illustrate it with one simple exercise. I'm going to show you a series of numbers. The numbers are... Okay, this is a quiz. What were those numbers? I suspect that unless you just wrote them down or are a very unusual individual, you would be very hard-pressed to reproduce those numbers from memory. The reason for that is very simple and very obvious. The numbers don't mean anything. You tried to learn the sequence of numbers by strict memorization, and learning based upon strict memorization has a very low probability of being successful in the long term. Sometimes you have no choice. If you want to name all the presidents of the United States in order, you don't have much in the way of other options. You'll just have to memorize them. That's okay. Sometimes you just do what you have to do. But suppose I let you in on a little secret. Suppose I told you that this was not a series of random numbers. There was a rule for generating these numbers. The rule was start with 1, double and add 1, 3. Double and subtract 1, 5. Double and add 1, 11. Double and subtract 1, 21. Double and add 1, 43, etc., etc. So the rule is simply start with 1, double and add 1, double subtract 1, double and add 1, double and subtract 1. Now, I'd be willing to bet that you'd be able to regenerate the series of numbers with little or no difficulty. And suppose I said that there would be a quiz on the numbers tomorrow. If you had simply memorized a list of numbers, you most certainly would have to re-memorize them again, probably just before the exam itself. Indeed, it might be so difficult for some that there would be a temptation to cheat. But let's suppose, instead, that you learn the rule. Now, how long would you have to study? Not very long, if at all, and you'd get an A for sure. And suppose a week later or a month later or whatever, I gave an unexpected pop quiz on these numbers. Once again, strict memorization would probably result in limited, if any, success. But if you had learned the rule, things would be completely different. There's a very high probability that you would remember the rule a week later, perhaps even a month later. And what if you were forewarned about the upcoming quiz? Those who only memorized the numbers would be back to their notes, frantically searching, trying to rememorize the list. Those who learned the rule might, at most, have to take a quick glance back at it. For the memorizers, this is a difficult course. For those who understand, it's almost comically easy. Obviously, knowing a rule is a whole lot better than trying to memorize a random series of numbers. But what if I came to class the next day and said that we were going to learn a second series of numbers? Some students were just told the numbers, while others were told the new rule. For our next series of numbers, our new rule will be start with 1, square, and subtract 5. Okay, 1. 1 squared is 1 minus 5 minus 4. Minus 4 squared, 16 minus 5, 11. 11 squared, 121 minus 5, 116, etc., etc. I mean, once again, given a calculator, I suspect that you would be extremely successful at producing this series of numbers. But what does it have to do with chemistry? Quite a bit, actually. We have seen two ways of trying to learn something. The first way was by rote memorization. I will sit down and I will run through this list and I will run through this list until I know it. And you can be successful with this method, but boy, is it difficult. The second method is better. I know a rule. Well, actually two rules. Double 1 and add 1, double and subtract 1, and square and subtract 5. Now let's imagine, for whatever bizarre reason, that you were taking a course that required you to reproduce different sets of numbers. One group of students approaches the course by simply trying to memorize each different set of numbers. The second approaches the course by learning the different rules that are used to generate the different sets of numbers. Which group do you think would be more successful? I would suggest that the answer is obvious. But what if a new set of numbers was presented, let's say, every day? Now how would each group do? I think the group trying to memorize each and every different set of numbers by rote would have, to say the least, an almost impossible task in front of them. Oh, I mean, it's possible there might be a few students with exceptional memories and or outrageous work ethics that might possibly succeed, but most would almost certainly be doomed to failure. The group who were learning the different rules used to generate each different set of numbers would clearly have a much better chance of being successful. But of course, even learning all these different rules, while much more efficient, would still be a challenging task as the number of rules grew. What we would really love to have might be called a rule of rules. In other words, a master rule that would tell us how each successive rule was created. It would tell us how each successive rule was related to the previous rule. If we knew this rule of rules, then we clearly would have it made, so to speak. I mean, we would hardly have to study at all and would be virtually guaranteed to get an A in the course. Unfortunately, for what I've given you here, I mean, there is no rule of rules. Now, if chemistry were the type of subject for which there was no rule of rules,